get the slideshow set up and go from the current slide. So I think we've already done the current slide. I've been trying to find it here. I don't see it listed as that, but I think we did do it. Now, let me go over a few things first. Now, number one, did y'all get the message about the class on Monday? Y'all came? And some of you went to Dr. Bryant's class, but I only had 4 people that signed up there. Yes? Yeah, but I think you signed up, didn't you? Right. But only 4 people. He gave me a list of only 4 people. So I appreciate that y'all did try to go. I'm sorry. She let us know. She sent us an email Sunday morning. Of course, I didn't see it until Sunday afternoon. And then immediately I started sending out the things on Blackboard. So you got it just about as soon as I did, as I saw it. And then I was there until almost 5 o'clock. And then came over for my 5:30 class. Okay, Essence is here. Okay. Now, for the rest of the term, I hope there's not going to be any more surprises like that. Let me give you a couple of minor changes. I doubt if it's going to bother anybody, but just let you know. Next Tuesday morning, I have a doctor's appointment. I don't know if you remember, maybe at the first of the term, I told you I see a hematologist, and he only sees patients on Tuesday mornings. It's the only time. I can't go in for Fridays or some other time that's more convenient. Only Tuesday mornings, the only time he sees patients. So I've got the appointment at 8:40. I have to be there for labs at 7:40, so I'm basically going to miss my entire differential equations class. So I arranged with them that I did half of the class that I'm going to miss next Tuesday. Well, I got half a class done extra yesterday. I'll do the other half tomorrow, which means that normally on Tuesdays and Thursdays, my office hours are 10 to 12 and 3:30 to 5:15. Tomorrow it'll be 11 to 12 because I'll be doing an extra hour, 55 minutes of class. So it won't be quite 10 to 12. It'll be 11 to 12. Now, I think I had told you earlier that a lot of Tuesdays and Thursdays I stay later than the 5:15. I think for the rest of the term I'm going to have to leave at 5:15. I'm volunteering for a group, and they want to meet every Tuesday and Thursday at 5. I said, I can't possibly do that, but I'll get there as soon as I can. So I got to leave at 5:15 to get to Birmingham as soon as I can. So I won't be staying late most nights, if any nights, Tuesday and Thursday for the rest of the term. Anything else? There is one other event coming up, but I think it's on a Tuesday or a Thursday. So I don't think it'll interfere with this class, but it may mess up office hours. I'll let you know as soon as I confirm in my mind when that is. All right. So I hope for the rest of the term we'll have class twice a week. Now, from now on, we've missed 4 Mondays. That's made this an 8-week term rather than a 10-week term. We had Memorial Day off. I had to be in New Orleans on a Monday. When I requested to have the trip go on a Friday, Saturday, the vice president changed it to Monday, Tuesday, and I couldn't get out of it. Then the governor gave us Monday off before 4th of July, and then the dean took away the Monday this week. Okay, so that being said, any questions on anything we've covered so far? Okay, yeah, I have found the impulse momentum theorem. I don't think we've gotten there yet. We're on Quick Quiz 6.1 at the top of page 162. We're in topic 6, momentum, impulse, and collisions. And we're actually in section 6.1 still, and we're on Quick Quiz 1. okay? I don't know if many of you have books, but let me hit this. Two masses, M1 and M2, when M1 is less than M2. Smaller mass is M1. They have equal kinetic energies. Equal kinetic energies. How do the magnitudes of their momenta compare? They have M1 is less than M2, but they have equal kinetic energy. Okay? Now, the A option here is not enough information is given. B is the momentum of 1 is less than momentum of 2. C is momentum of 1 is equal momentum of 2. And D is momentum of 1 is greater than momentum of 2. So let me jot down, because some of you don't have books, what the situation is. Here we have mass 1. Let me get my pen activated. We have mass 1 less than mass 2. KE1 is equal to KE2. Got it? That's what they said. And how do the magnitudes of their momenta compare? A, not enough information. Okay. B, C, and D are this. Momentum 1, momentum 2, and the B one is less than, the C one is equal to, and the D one is greater than. Okay. Okay, good deal. All right, there's the deal. We know that the mass of object 1 is less than the mass of object 2, but we know kinetic energy of the two objects are the same. So the question is, how do the momenta compare? A says there's not enough information. B says momentum 1 is less than momentum 2. C says it's equal to momentum 2. And D says momentum 1 is greater than momentum 2. What do you think? What would be your guess? Quick quiz 1, top of page 162. Okay. Let me suggest to you the key here. If the kinetic energies are equal, that means 1/2 m1 v1 squared is equal to 1/2 m2 v2 squared. Would you buy that? That's what kinetic energies are, right? Okay? We can multiply both sides by 2 and get rid of the 1/2. Okay? That's an equation. But we know that M1 is less than M2, right? By that? That's what was given. M1 is less than M2. Therefore, I contend to you, if the kinetic energies are equal, that V1 squared must be greater than V2 squared. Wouldn't you say? Okay. The question is by how much? Okay. I'm actually going to make that an equality here. Okay. I don't know if this is going to be helpful or not, but I'm going to do it. V1 squared is equal to M2 over M1 times V2 squared. Okay? And we know that M2 is greater than M1. Okay. So that means that velocity 2 is obviously greater than velocity 1. So let's take a square root of both sides. So we got V1 is equal to the square root of M1 over M2, right? M2 over M1 times V2, taking the square root. That means that the square root of M1 V1 is equal to the square root of M2 V2. So let me write that again. The square root of M1 V1 is equal to the square root of M2 times V2. Do you see that? Now, we know that M1 is less than M2. Is it enough to make a difference? Okay. These are momentum. I'm tempted to say not enough information is given. I think if there was just a little bit of difference there, like if M1 was a small number, say less than 1, and M2 was also, then I don't think you could say, but M1 was a huge amount different from M2, maybe something different. I don't know. I would think right off the top that V1 would be significantly larger than V2. So it's either, I think, A or D, but I can't definitively say one way or another. Anyone want to make a guess? Topic 6, and I said it backwards, is actually less. Okay? That square root of M1 that V1 isn't enough larger than V2 to make up for the difference. So it's actually less. That was a tough one. I think one of the toughest they've given. All right. Now let's move to this one. Now I can't remember how far and how much we said about this last time. But if you remember, I hope I at least said this much. Your force, the net force of that an object is exhibiting is equal to the mass times the acceleration of that object. Where do we get that? Newton's second law. That's what Newton's second law says. Now remember, I said, I'm pretty sure, that this could be written as m times delta v over delta t. That's what acceleration is, where velocity is a vector also. And that can be written as delta mv over delta t. What is delta mv? Change of momentum. Mass times velocity is momentum over delta t. Now take that equation, multiply both sides by delta t. Pretty sure I did this before. And that gives you that F delta t is equal to your change of momentum. Oops. Okay? Now, or the other way to phrase it is that this way, net force by the way, is equal to the time rate of change of momentum, which is how I'm guessing Newton described it. You know, in his Principia, he talked always about the quantity of motion, which was momentum. I don't know if he named it, but he called it the quantity of motion as the product of mass times velocity, and the time rate of change of that quantity of motion is the net force action. That's the simplest way to state. I think it's just as simple as this one, probably a little more so. We're used to saying force equal mass times acceleration, which is definitely true, but it's also the time rate of change of momentum. Okay. Now, written this way, this is what we call the impulse. Okay? And the impulse is the change of momentum. And that's what we've got up here. The impulse momentum theorem states that the impulse acting on an object is equal to the change of momentum of the object. And what is that impulse? The product of the force times the time interval. Okay? And I talked, I think, some about hitting golf balls and tennis balls and baseballs and all sorts of things in terms of changes of momentum or forces. Okay? So that would be mass times final velocity minus mass times initial velocity. That's your change of momentum. If the force is not constant, we use the average force applied rather than the constant force. Okay? And again, the units are kilogram meter per second. Okay? Momentum is kilogram meter per second. Impulse would be kilogram meter per second. And this is where the second set of units come from. You could say this is the same as a Newton second. Okay? So momentum could have the units. Kilogram meter per second is the fundamental set units. You could also call it a Newton second. All right. Any questions on that? Now, here's what we mean that you could use the average force if you had a variable force. The average force can be thought of the constant force that we give the same impulse or change of momentum to the object in the time interval as the actual time varying force gives in the time interval. Okay? So what they're saying, if you have a variable force, this is force in the vertical axis, time in the horizontal axis, and this was your variable force. It started at 0, peaked at a fairly high force, came back to 0. For some reason, I can almost imagine hitting a drum. Okay, when you first make contact with the drum, maybe you're just barely touching it, then you hit it, and then ease off of it, and do like that. So you almost have this kind of a peak. Well, what is that equal to? The average force over that time interval times the time interval. As long as this area and that area are the same, you can use this average force rather than the variable force. So that gives you a little flexibility, and you don't have to do integration, which is basically how you do the first one. Since you all have been required to have calculus, you probably, some of you may not know how to do that. Okay. There is an interesting looking figure here. Let's go on and finish with average force, I guess. The impulse imparted by a force during the time interval delta t is equal to the area under the force time graph from the beginning to the end of the time interval. Or the impulse is equal to the average force. That's the same thing we said before, multiplied by the time interval. So either way you want to do that, you can either calculate the area under the graph or make it equal to the average force over that time interval. Now, before we proceed with that then, there's an interesting figure at the top of page 163, figure 6.2. An apple is being pierced by a 30 caliber bullet traveling at supersonic speed of 900 meters per second. This collision was photographed with a microflash stroboscope using exposure time of 0.33 microseconds. That's pretty quick, okay? And shortly after the photograph was taken, the apple disintegrated completely, okay? Note that the points of entry and exit of the bullet are visibly explosive. You can tell stuff's going on there. Okay. Now, there's an Applying Physics 6.1, Boxing and Brain Injuries. I know a lot of people follow boxing and may even like boxing, but there have been, we think of football having an undue amount of brain injuries, and it does, okay? They're constantly trying to improve helmets and things like this. But in the world of boxing, especially professional, there is no head protection. And that's where I think most of the blows go. Some people pound on the body for a while, but usually to get the knockout punches, you're hitting the head. And I don't know if y'all remember the 1996 Olympics in Atlanta. Who lit the torch? Muhammad Ali. And he was, at his time and at his peak, pretty much undisputed the greatest boxer in the world. You remember him lighting the torch? He had Parkinson's so badly, it was really, people were worried that he was even going to be able to walk up to it and light it. And he wasn't really all that old. He's, I guess now, has he died yet? I thought he had. Okay. I don't think was much different from my age, and he was deteriorating pretty badly, and I don't think anyone begins to separate that, he just happened to have Parkinson's. I think it was induced by all the head trauma that he had. So, a good little, not a very pleasant sounding one, but a good little blurb there. There's also one on teeing off. And for those golfers in here, there's another pretty good one to take a look at. Okay? That's actually example 6.1. So if you wanted to see that, you certainly could. I'll be glad to go over that. There's also example 6.2, how good are the bumpers? And I went to a math meeting in Shelton State, I think it was. I don't remember for sure. I believe that's where it was. And the speaker there was an engineer the main speaker was an engineer from Mercedes, I believe it was. And he was describing, and I found it almost hard to believe until I really thought about it and said, no, that's really what it was. In the past, they built cars to protect the motors. Not the motorists, the motors. Because you had all this very heavy-duty, rigid equipment around the motor to keep that from getting damaged. And the passenger compartment was basically compressible. Okay? And when you had accidents, things compressed into the into the passenger compartment, and people got killed or maimed or damaged pretty severely. Nowadays, supposedly from what he says, everything else is compressible, and they try to maintain the integrity of the passenger area. That has the greatest support. Even the engines are built to collapse, and certainly the bumpers are. I can remember back when I was young, most of the cars had those big, fancy, nice-looking, bright and shiny chrome bumpers. Okay? Those were as hard as a rock. There was no give on them at all. When you were in an accident, they pretty much kept their shape. The passenger compartment, it folded. Nowadays, the bumpers are not made out of metal. They're made out of some type of plastic, many of them having compressible cylinders that allow the bumpers to compress slowly and then release. That cuts down on the force due to that you would experience inside the canopy of the compartment, passenger compartment. So that's example 6.2. Well worth a look. So let's move on to injury during automobile collisions, okay, which is a lot of what we've been talking about. Let's look at an impulse applied to auto collisions. The most important factor in an auto collision time is the auto collision time, or the time it takes the person to come to rest. Now let's go back again in the past. I told you about the bumpers. Let me tell you about, y'all might remember some of this, I doubt it, unless some of you have some vintage cars. I can remember when I was young, typically I don't know what to say first, but typically the dashboard was metal. Okay, everything was metal in the car. The steering column was pretty rigid. The dashboard was metal. Everything was metal. There were no seat belts, not even optional. There were no airbags. So when you were in a collision, they called the passenger seat the death seat. Because if you were in a collision, that passenger was going, okay, here was a car moving at, say, 60 miles per hour. That's the velocity. Enormous mass, okay, moving at a high rate of speed. The momentum was very large. You hit the tree, you hit another car, whatever has gotten hit here, then you're changed to zero velocity in a very short time limit. And if that change of time and the passenger was sitting here and the car stopped and he didn't or she didn't, then into the dashboard, into the windshield. Your time of collision that they're talking here, the collision time was minuscule. Thousandths of a second, something like that. It's very small. Therefore, if you look at the formula, impulse, that's force times the time interval is equal to the change of momentum. We know the change of momentum is huge. Large to zero. Large change of momentum. If this time interval is very, very small, that means the force is even larger. And that means broken bones, mutilated bodies. I mean, it's awful. Now, I can remember, I don't remember what type of car, what model it was, but it was a Plymouth, if I'm not mistaken. My dad only bought used cars, okay? It was really late in his life before he ever bought a new car. I can remember one new pickup he bought, but generally those were used too. He got a better deal, okay? And I remember this Plymouth, first one that we had, it had a layer of cushioning on that metal dashboard. Still a metal dashboard, but the cushioning was on it maybe an inch thick or something like that. So that meant when the person was hitting the dashboard, still no seat belts, still no airbag, when the person was hitting the dashboard, there was a little more time for him to compress that cushion before he reached the metal and then come to an abrupt stop. If that little bit of time was even something like, got you down to 1/10 of a second rather than 1,000th of a second, you have just decreased the force by a factor of 100. Decrease the force by a factor of 100. Okay? Then the next improvement they came up with was, I don't remember the exact order of these, but I'm pretty sure of this, that Darius is here. Well, I've just got to find you. I know you're in here somewhere. There you are. What's that? Okay. And somebody else said that also, didn't you? Okay. Oh, yeah, but you weren't here. Someone came in before class. Who was that? Oh, it was Brittany. Miss Humes, Courtney Humes, right? You said you needed. Yeah, stuff. Okay. I'll get those at a break or sometime. Okay, so here we have, first improvement I remembered was cushioning the dash just a little bit. Okay? But it was a huge, huge help. Okay? Now the next thing, I don't know, remember all the order, but one of the next things was seat belts. Okay? Increasing this time, that time of collision, the collision time, or the time it takes the person to come to a rest, any increase you can do on that will reduce the chance of dying in a car crash. So one of the other things was then seat belts. When they finally got seat belts in, the car would come to an abrupt stop, and you would go forward, but then you wouldn't go all the way, and it would pull you back. So you were prevented, hopefully, from encountering that dashboard, whether it had metal or cushioning or whatever. Along about the same time, they went away from metal dashboards and started making them plastic and not as sharp and that kind of stuff. So they would give not your bones. Okay, that was a good thing. And sometime also they made the bumpers so they were somewhat collapsible, plastic so they would bend rather than hold steady like those old chrome bumpers did. And also they introduced those basically almost like a shock absorber behind the thing so the bumper would give some and then go back. Basically, they were only good for like 5 or 10 mile per hour crashes, but they would help some. Then they came out with seat belts, and then finally airbags. Now, I have had the misfortune of being in one crash that the airbag did, activate. That was the first year I was teaching at Jeff State. I was adjunct there, teaching developmental math. And I got up, the shortest way for me to go to the campus was sort of back roads, but it wasn't necessarily the fastest way. And we didn't live too far from the expressway, and my initial departure from the house, I could see the traffic on the expressway. And early in the morning, sometime it was really slow. And it had rained this morning that I'm talking about. No one was expecting. It had been a while since we had a rain, but it had rained, but then the rain had stopped. And Ryan came. Okay? And I looked, and there was hardly any cars on the expressway. Like I said, I could see the cars moving, and they were moving along really nicely. I said, hey, I think I'll get on the expressway. The rain may slow down on the surface, so let me get on. So I got on the expressway, and shortly I had to speed up because there were cars coming. Had to get up to speed of those cars. Just about that time, crested a hill. And immediately on cresting the hill, all I could see was red lights. Everybody was braking, and the two cars ahead of me swerved to get into this lane. The car ahead of me swerved to the right to get in that lane. There was a car in my lane, and they just took up the other two lanes, slamming on brakes at the same time. I slammed on brakes. I had nowhere to go. it had just rained. The car hydroplaned right into the back of one of those cars. Again, I wasn't going super fast, but it was just enough to activate the airbag. I didn't even realize it had activated. It was that quick on it. The next thing I knew, this thing was in my face, and it went down, and there I was. Not that much damage to the car, and yet, this is sort of the downside, that totaled the car. A little bit of damage to the front fender, not too much. They could have fixed that pretty easily, but the airbag, to replace the airbag, was going to put it over. It was an older car, and that was going to put it over the amount that the car was worth. I thought, oh my goodness, but great things they are. I did not touch anything that was going to give me any problem. This steering column, nothing. I didn't come close enough to touch that. The airbag did deploy, not a scratch, but a total car. What's that? I'm sorry? Yeah, it's a really good thing. All right. Oh yeah, definitely. Tiara, is that right? Huh? Brianna, sorry about that. There you are. All right. Has anyone else come in since the call roll? Okay, so these, the whole purpose, every one of these steps kept increasing that time interval over which the change of momentum occurred. And every time the time interval increased, the force decreased. Because this stayed the same, the delta P. Now, I wasn't going that fast, so the delta P wasn't that fast to begin with, but this lengthened the time interval so that the force was negligible. Because the airbag, I had to crash into the airbag and it pushed me back. Yes. Okay.
That meets at 2 o'clock. I need to speak to one of her students.
Okay.
The location.
Yes, I'll try to do that. It's not far. It's about all of that. Sorry about that. Okay. So that's where the safety comes in. Now, there is sort of an example. If there's injury to pass in a car collision is given here. See, here it is. Here's a typical collision values. Okay. Now, I don't know if you know about what your mass is in kilograms. I don't know myself. I don't think in terms of kilograms, but for a 75 kilogram person traveling at 27 meters per second, by the way, that's 60 miles per hour. So on the expressway, this would be slow. On a surface road out in the country, that would be about average. Okay? Coming to a stop in a hundredth of a second. Now, these zeros are not significant. That one is. So there's 2 significant digits there, 3 significant digits there. The typical force is about -2 times 10 to the 5th newtons. Okay? That's the force acting on you this way and making you stop. The acceleration, I was going to say, why have they got anything in grams? That's not, and why did they call it A? That's acceleration would be 280 times the acceleration due to gravity. That is a lot. This is 9.8 meters per second squared, and that would be 280 times that. those are almost certainly fatal. 60 miles per hour coming to a stop in 100th of a second. There's no way that any body can sustain that. Okay? That's if they stopped in 100th of a second. And that would be about like having maybe a padded dash would be about all. Okay? Boy, is that all they're going to say then? Basically, they just summarized the data they gave on page 165. Okay? And what they conclude here, if the time can be increased by 10 times or even 100 times, the value for the 100th of a second for a hard collision moves up to being, say, a 10th of a second to even 1 second. Okay? And that makes the contact force 10 to 100 times smaller. Seat belts restrain people so that they come to rest about the same time it takes to stop the car, typically about 1500ths of a second. 1500ths rather than 100th. So that's 15 times, reducing the force by 15 times. Okay. Oh, and that's what we were just talking about here. The seat belts restrain people so it takes more time for them to stop. The new time is about 1500ths of a second. That's 15 times as long. The new force is about 9.8 kilonewtons. Let's see what the previous force was. That was 2.0 times 10 to the fifth. That would be 2, 0, 0, comma, 0, 0, 0. So that would be 200,000 newtons of force. Nobody can withstand that. If you divide that by 15, you're on the order of 9.8, 9,800. So rather than 250,000 newtons, you're at 9.8 thousand newtons. So you've reduced it big time. About 1 order of magnitude below the values for an unprotected collision. So that first example was unprotected. This one is protected. Okay. 15 times the length, delta T, divide the force by 15. I'll take it. Okay, airbags, they increase the time of the collision. It will also absorb some of the energy from the body. It will spread the area of contact, so it's doing a lot of things, decreasing pressure. Now, does everybody know what pressure is? What's your definition of pressure? Okay. If you're measuring the pressure of air in your tires, what units do you usually use?
Square inch.
Second?
Pounds per square inch.
Okay, what does pound measure?
Weight.
Or force. Yeah. And square inch measures?
Square inch should be not volume, but would be displacement. No.
Area. Square inch is square. How much area is a piece of paper? Square inches. Okay. So is force per unit area. Okay. I heard about this. I wasn't involved with it. I went to grad school in Lincoln, Nebraska, University of Nebraska-Lincoln, and I crammed the 3-year program into 5. So I was up there for a while, and someone told me, I was surprised at it, it seemed like Lincoln, Nebraska was the capital of waterbeds. And they said they figured that must be people were so far from either ocean, they just wanted to be on the water. So they had a lot of waterbeds. And this one company, rental company, didn't want students bringing waterbeds in to their apartments. So they wrote in the contract, because of the greater pressure water bags are not allowed. So good old student did the calculations and found out that water beds typically had less pressure. Because if you think about it, what they meant to say was because of the added weight, but they used the wrong word. They said pressure. Water beds set flat on the floor, so you have that heavy weight, but it's scattered over a huge area. Whereas a conventional bed, much lighter, but all the weight is on four little diameters like that, where the four posts of the bed hit the floor. The pressure on that was much greater than the pressure on the water bed that scattered it over the whole thing. So when it says spread out the area of contact, you can't increase the area, you decrease the pressure. So the student presented that and showed his figures, and they had to let him have the water bed that year. Of course, the next year they had changed the wording to because of the added weight, you cannot have water beds, and then you couldn't have a water bed anymore. Okay, but it decreases the pressure and helps prevent penetration wounds. I've heard back in the old days that sometimes people, even the driver, hit the steering column, and those steering wheels were very hard, and the column was not at all flexible. Nowadays they do sort of give some, but back then I can remember people talking about having bruises. They could see the steering wheel, the bruise pattern on their torso after a very minor accident, and sometimes the ribs that were broken were in the pattern of the water of the steering wheel. But this helped prevent that because it spread the force over a larger area, decreasing the pressure on any particular part. So airbags are definitely positive things for safety. I also remember my older brother, he had just gotten out of the Navy, I think, and I think that was the reason he didn't have a car yet, because he had sold his before he went in, and he hadn't got one to come out, so he borrowed my younger brother's car, which was a fairly new car, not brand new, but fairly new, a much nicer car than we usually drove, but my younger brother was a little bit bigger spender than the rest of us. He was borrowing money like crazy, but just a bigger spender. And so Mike had borrowed Dan's car to come home, and he was really exhausted. And he made it to within almost sight of the farm and fell asleep. It was late at night, ran into the ditch, and he happened to that time. He had always hated wearing seatbelts. For some reason, he had put them on that time. Maybe the newer car almost made you wear it, and he realized he would have been severely damaged without that seatbelt. This was before airbags, and that convinced him for the rest. As far as I know, to this day, he never is in a car without a seatbelt on. So they do make a big difference. All right. Too much of that, probably. Let's move on to 6.2, which is conservation momentum. Momentum in an isolated system. Now, what do we mean by an isolated system? Any ideas? Isolated system means no net forces coming in, no net forces going out. All the forces are contained within the system. That's what we mean by isolated system. In which a collision occurs. The collision may be the result of physical contact between two objects, that could be your collision, or the contact may also arise from electrostatic interactions of electrons in the surface atoms of the bodies. And there also could be collisions that are magnetic in nature. In fact, when you have sort of magnetic collisions, and also possibly the electrostatic ones, the magnets, say light magnets repelling each other, they force them to stop without actually touching because it's a field situation. But the isolated system will not have external forces. You can't external forces coming in, that would be an isolated system. But if all the forces are contained within the system, you got it not. Okay? And as long as that is met, momentum in an isolated system in which a collision occurs is conserved. The initial momentum has got to equal the final momentum. Now, remember, momentum is what kind of quantity? Vector quantity. Okay? So when you're adding up the initial momenta and the final momenta, you have to add them vectorially. Have any of you ever played pool, billiards? Okay? What is your initial momentum of that system usually when you start the game?
Q, like the Q.
Yes. You have the balls racked. 15, is it?
Yeah. Yes.
Yeah, 15 balls in the rack. You have rack move. And the only momentum in the system is in the cue ball. You hit it, usually pretty hard, right? Give it large velocity and decent mass. That's the whole momentum of the system as it's on its way before it touches that one ball or whatever it is at the very point there. Okay? Then, as soon as it hits, is there any momentum lost or gained? No, because momentum is conserved. You have balls flying all over the place, okay? But the total momentum of the system is conserved. For every ball heading this way, there's another one heading that way. You have, if all the momentum is that cue ball coming down the table like this, that's the total momentum afterwards. So for any momentum this way, you've got to have momentum that way, equal and opposite. Because the total momentum of the system still got to be that one ball coming this way. So yeah, they all move and they all move pretty fast. Some up bounce back and stuff like this. Momentum is conserved. Okay. The principle of conservation momentum states that when no external forces act on the system, so of course you hitting the pool ball, the cue ball, that's an external force. But as soon as that hit is over with, the total momentum of the system is the motion of that cue ball. Okay? Consisting, with no external forces act on the system, consisting of two objects. Now they're talking about two objects, that's a little easier to deal with, that collide with each other. The total momentum of the system remains constant at every instant of time. Specifically, the total momentum before the collision will equal the total momentum after the collision. Always, unless you have some sort of external forces. Now, what kind of external forces could you have?
Friction.
Friction. That's the biggest problem, okay? But generally they're not. Now, with billiard balls, round balls rolling on a fairly smooth table, level table, you minimize that pretty much. I guess the felt is part of that. But since you hear the colliding balls, you know some energy, some forces are making those sounds. So you know there's a little bit of loss. Not a lot, but a little bit. Okay. Now, conservation of momentum, an example. And I'm trying to see where this is in the text. I don't see it in the text. So I'll just talk through this one. This is from the earlier slide set. They don't show this one anymore. It's basically very similar to what we saw before when we were talking about average force as opposed to, in fact, it's basically the same slide. The momentum of each object will change, the total momentum of the system remains constant. The impulse equals the area under the force versus time curve. The impulse of the average force equals the impulse of the actual time varying force. That's basically the same figure they're showing here from what we had before. I'm not sure they got the right figure on the right slide here. Okay, the words don't really say a lot. They're true, but it's hard to distinguish whether those are the right words. Now here they do have it. Now my guess, what they should have had rather than these two, if you got your text, you see the two balls colliding on page 166 in sort of the margin notes. Actually, some of that would come from this. The A picture there, 6.6A on page 166, that shows when the collision may be the physical contact from two balls, okay? Two objects, okay? The B there would be electrostatic contact that would be between two objects that are oppositely or similarly charged, a proton and the nucleus of a helium atom, okay? And I think the figure 6-7 is what these last two slides were showing. Before the collision, you have M1 and M2. M1 smaller, M2 bigger. And they both seem to have the same velocities, but going toward each other. So one is a positive, one is negative, whichever way you define it. After the collision, when they collide, the smaller ball is going to pick up greater velocity. The larger ball reduces its velocity. We will see this in the lab. I don't know if we'll get to do the lab today or if it'll be next time. Okay? But that's basically conservation of momentum. Now, the equation is not numbered, but it's at the bottom of page 166. Change of momentum, the force of ball 2 on 1 times its time interval is equal to minus the force on 1 on 2 over its time interval. And basically, this figure kind of says it. The force on which object 1 acts on object 2 is always equal and opposite to the force on which object 2 acts on object 1. What is that a statement of? Who do we name a force after? Newton. He came up with a set of laws, remember? Which law is this? Second? That's the third law, because these are two different objects. Object 1, object 2, forces on different ones, and this figure describes exactly what's happening there. If object 1 is hitting object 2 is being hit by object 1, the force of 1 on 2 would be positive, the force on 2 on 1 would be negative, meaning one's going to go one way and one's the other. The impulses are also equal and opposite, okay? Because impulse is change of momentum, and the momentum is conserved. Forces are not usually conserved. This happens to show that in this case they are, Newton's third law, but the momentum are always conserved as long as there's an isolated system, no net forces coming from the outside. Okay. Here we have it. Looking for this formula. Page 167. This is basic. Sorry. Basically saying what we just said. What does the I stand for? Initial. L stand for final. This says as long as you have an isolated system, the total momentum before the collision and has to equal the total momentum after the collision. Again, our lab today, or next time, whenever we have it. What is the total momentum? You have two objects that are going to collide. The momentum of ball one, let's call it balls, is the mass of ball one times the velocity of ball one initially, plus the mass of ball two times the velocity of ball two initially. Now let's assume that they're coming in opposite directions. That makes one of those two negatives, right? Okay, so, but whatever you had initially, no matter what way they take off or go, the mass of ball one times the final velocity of ball one plus the mass of ball two times the final velocity of ball two. That sum has to be the same size. Momentum is conserved for the system of objects. Does that mean ball one maintains? No. That means these could be very, very different. These could be very, very different. It's the sum of this has to equal the sum of that. The system includes all the objects interacting with each other. So the pool ball example, what is that, 16 balls total. The cue ball initially has all the momentum of the system. After it collides and they bounce around and stuff, the total momentum of that system is still equal to the momentum of the cue ball. Now, sort of clogging up, I don't know why. This assumes that only internal forces are acting during the collision. Okay? In other words, you don't have any outside forces, no one bombing you with another ball somewhere there. Embry, right? Okay. There you go. All right. Now, you can generalize this. This is a two object system. You can have a system with any number of objects, like 16 objects in a pool table. Okay, those balls, cue ball plus 15 pool balls. You could summarize all those as well. Okay. Now let's look at different types of collisions. There is a figure here, an example here, it has a figure associated with it of the archer, and you can read that. It's pretty straightforward, I think. I'd be glad to do it if anyone needs me to do it. I don't see these particular words. They certainly are. Oh yeah, here they come. This is under 6.3, collisions in one dimension. So the archer, if anyone wants to see that done, I'll be glad to. Before we move to 6.3, here's another quick quiz. Quick quiz 6.2. A boy standing at one end of a floating raft that is stationary relative to the shore walks to the opposite end of the raft away from the shore. As a consequence of the raft A, let's see, let me back off and see if a little more room here. So, I draw lousy pictures, as you have noticed. There's your level of water. Here's the raft on the water. Okay? Boy is standing on one end of the raft. Okay. There's a guy on one end of the raft. And this raft is initially stationary. relative to the shore. Is he walking? Here's the shore over here. Okay. And initially, the raft at rest. Not moving initially. Okay. Okay. Catch some of the words that are a little key here. A boy standing at one end of a raft, a floating raft that is stationary relative to the shore, walks to the opposite end of the raft away from the shore. Okay? What's the initial momentum of that system? The boy is standing, so he's at rest. The raft is stationary, so it's at rest. The initial momentum of the system is 0. No motion going on there at all. Now the kid walks to the other end of the raft away from shore. What does the raft do? Take it? Okay, it moves. Is it going to tend to move? Okay. So the boy moves, walks away from the shore. He now has a momentum to the left. What does that mean the raft has to do? It has to move toward the shore. Now they haven't given any masses here, so I'm trying to figure out if they're going to enter that into the problem. I guess not, okay? As a consequence, the raft A remains stationary, B moves away from the shore, C moves toward the shore. What you think? I think you just answered it, didn't you? Moves toward the shore. So that had better be C. Okay? 6 to C. Perfect. Okay. All right. Now we get to types of collisions. Okay. I was looking for this earlier. It doesn't list it as types. It just says collisions in one dimension. I didn't think that was the right one, but that is. Guess what?
Do we have a lab today too?
I don't think we're going to get to it. I had hoped we would, but this is a little bit longer chapter than I was imagining it to be. So it looks like we probably won't get to it today. We might finish the chapter before the day's through, but if so, we'll move on to we're probably going to skip, if I remember right, we skipped 7 and 8. Because we've got to cover fluids and solids at topic 9. For those who did come, I think Dr. Bryant said he was already into that. Is that what y'all talked about last time? So I don't think I have time to do 7 and 8, so we'll just move on to 9. So let's see what we can get finished here. The title of this one is Types of Collisions. In your book, it's collisions in one dimension, but then it talks about the types. Momentum is conserved in any collision. What's the requirement? Isolated system. Okay? As long as the system is isolated, momentum is conserved. And here they're going to introduce 2 or more types of collisions. It depends on how you define it. The first of these is an inelastic collision. Now, what do we mean by that? What does it mean to be elastic?
Elastic is when it bounces off each other, and elastic is when it sticks together.
Okay, you got it.
Yeah.
The elastic means there is no change of shape at all, or at least permanent change of shape. Everything rebounds perfectly. So an inelastic collision would be when there is, when they, like you said, stick together. And when you have an inelastic collision, your kinetic energy is never conserved. Okay? Some of the kinetic energy is converted into other types of energy, such as heat, sound, work to permanently deform the object. Any of those things would happen. I think, do any of you remember silly putty? Okay, silly putty was this stuff that if you, I don't know how to describe this best, if you had a wad of it and threw it against the wall, it just would lob and stick to the wall. Okay, that would be an inelastic collision. Kinetic energy would not be conserved. Now, a perfectly inelastic collision, that's why I was wondering how they were going to do this. The collisions occur when the objects stick together completely. Like the silly putty doesn't bounce off the wall at all, it sticks. Okay? And in this case, not all of the kinetic energy is necessarily lost, but some of it will be. Okay? Now, the more classic examples of that would be railroad cars. Okay? If this railroad car was rolling down this way, and this one, say, was stationary, but when they collided, if they had bumpers on them and they bumped away, that may be elastic collision. But if they have couplings there, and when they went together, they were stuck and then stayed together, that would be what they consider a perfectly inelastic collision. Not all of your kinetic energy is lost, but certainly some of it is. Okay. The other kind is called elastic collision. Now, in an inelastic collision, momentum is conserved because it's conserved in any type of collision as long as it is a isolated system. There S is here. Okay. Little part of the alphabet is filling up here. That's good. Okay. But kinetic energy is not conserved. But in an elastic collision, both momentum and kinetic energies are conserved. Now, in actual collisions, most collisions fall in between elastic and perfectly inelastic, somewhere in between. In my mind, that makes them inelastic because they're not elastic. But you'll find maybe even the book or others saying perfectly elastic collision. Well, guess what? It's either elastic or it's not. Okay? You can talk about perfectly inelastic, meaning they actually stick together, but a collision in which things hit, crunch, and then bounce back a little bit, that could be that is an inelastic collision, but because they didn't stick together, it would not be perfectly inelastic. So, sort of some weasel words there. So let's look at perfectly inelastic collisions. Before we do so, there is another there is another quick quiz. A car and a large truck traveling at the same speed collide head-on, and they stick together. Their bumpers intertwine and they can't separate. Which vehicle undergoes the larger change of magnitude in the magnitude of its momentum? The car, the truck. The change in magnitude of momentum is the same for both, or it's impossible to determine without further information. which vehicle undergoes and there's FA. Okay. Just made it in for the class period. Okay. Actually, perhaps not. No. 150. Okay. So which vehicle undergoes the larger change of magnitude in its momentum? The car, the large truck, or the change of the magnitude of momentum is the same for both, or D, impossible to determine without more information? Which you reckon? A, the car, B, the truck, C, there's the same, and D, impossible to tell without further information. What you think? What do you think? Okay. A car and a large truck traveling at exactly the same speed collide head-on and stick together. Which vehicle undergoes the larger change of magnitude in its momentum? The car, the truck, the change of magnitude of momentum is the same for both, or impossible to determine without more information.
Possible to determine.
The which?
Possible to determine it.
Okay.
It's same for both.
Say again?
It's same for both.
It changes both, but you mean the same? Same for both?
The change would, yeah.
What's that?
Yeah, see the change in the magnitude.
Yes, the change would be the same for both, right. The same for both. I thought you said the change for both. Yeah, the same for both. You're absolutely right. All right, so now let's move to perfectly inelastic collisions. Here we do have the ball pictures on the side. That earlier slide was just messed up, I think. Okay. When two objects stick together after a collision, they have undergone perfectly elastic collisions. I've said it about 3 or 4 times now. Get the idea. Okay? Conservation of momentum still applies. What doesn't apply? If they stick together. There is no conservation of kinetic energy if they stick together. That only happens if you have perfectly elastic. This is not. This is inelastic. Okay. So before the perfectly inelastic collision, the objects are moving independently. The little mass M1 is moving at velocity dI to the left, to the right. Okay. The bigger mass M2 is moving with a slower velocity to the left at v2I. Okay? We're using x being positive to the right. Okay? After the collision, the objects do remain in contact. The system momentum is conserved. Momentum is conserved, but the system energy is not conserved. Okay? Now, total energy would be, but that system energy would not. Okay? Now, what is the final momentum? I kind of disagree with the magnitudes here. You would have a mass of M1 plus M2 times the velocity final in that direction. I do not see how that can possibly be true, okay? This, to me, would have to be a little bit shorter than this one was. It looks like to me they're almost the same length. That would be impossible, I think, unless the massive, no, it still would be impossible. Yeah. So I don't think they have the magnitude of the error right, but they got the general idea. Okay. So, in this case, the conservation momentum becomes initial is M1 V1I plus M2 V2I, remembering that V2 must be a negative quantity. But here's where the negative is. You don't put the negative there. And at the end of the system, the final system is M1 plus M2 times V final. That's it at the end. So M1 V1I, which is in that direction, plus M2 V2I, but V2I is in the negative direction. So that accounts for that. And this would be the total mass times V final. Again, I disagree with the length of the arrow, but the rest of the problem is fine. And where you can go with that is then divide both sides by M1 plus M2, and you get V final then. Okay. Now, remember, momentum is a vector quantity. Direction is important. Be sure you have the correct signs, and if necessary, be sure you break it into components. So far, we're not doing any component vectors, but you could. Okay. There is a very good example 6.4, the truck versus the compact, that was very similar to the questions we were asking. I don't know if my voice is going. Well, I can't see it now. No, I guess that was in the quick quiz. That's where it was. I was thinking it was on the slides, but it's not. Okay. Momentum is a vector quantity. Direction is important, and be sure you use the correct signs corresponding to that. Whatever you set up as your positive direction, then go with it. Okay. Now, if you have elastic collisions, I slipped up and said it just a moment ago, none of you caught me. I said perfectly elastic collision. That's almost redundant. If it's elastic, it's elastic, okay? It's sort of like a perfect circle. Well, guess what? If it's a circle, it should be a perfect circle. You can't have a dented circle. It wouldn't be a circle anymore. Okay, so that's what. For elastic collisions, both momentum and kinetic energy are conserved. Typically, then you'll have two unknowns. Okay? I'm saying what they were, but typically you'll have two. Then you have two equations. Usually you know your mass, 1, and usually you know your initial velocity, 1. You know mass 2, and usually you know initial velocity 2. Since you knew mass 1, the mass doesn't change. Mass is a conserved quantity. Okay? V1 final may be quite different from V1 initial. Velocity is not a conserved quantity. Okay? M2 V2 final velocity could easily have changed. Okay? And that's going to be true. Total momentum of the system before the collision is equal to total momentum of the system after the collision. Understanding masses don't change, but velocities very likely and do change. All right, now, because you've got elastic collision, kinetic energy is also conserved, which is 1/2 L1 V1 squared, V1 initial squared, plus 1/2 M2 V2 initial squared. That's your total kinetic energy before the collision. After the system, whatever it is, doesn't have to be a collision, but that's what we're mostly talking about. Yeah, collisions, okay. 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Kinetic energy is also conserved when there are elastic collisions. You solve the equations simultaneously. Okay. Now, I don't know how you are in solving systems of equations, but remember, the M1, 1/2, M2, 1/2, all those are constants. The only variable here is the velocity. Usually you know initial and you know final, so the only variables are V1 final and V2 final. Okay? You know the two initials, V1 and V2 initial. And this is one of those formulas that they don't mind just, sorry. So much drainage. Usually it's the final velocities you don't know. You could have other things you don't know, but then you'd have to know one of the things. Because when you have two equations, you gotta, if you have two unknowns, you gotta have at least two equations. So how do you solve them simultaneously? Well, one of the problems here, this is quadratic in the unknown, and this is linear in the unknown. So it's not particularly an easy thing to do. It's not like you could do set them up and eliminate a variable. You can, and you do that, but it's a little more involved than a simple series of equations because you've got your variables raised to powers. Okay. Now, they say a simpler equation can be used in place of the kinetic energy equation. Now, I wanted you, sorry, to show you where this comes from. Frankly, I would have broken these down a different way from what they do, but this is true, and you can use that. Sorry. I hate that they didn't show you how they got them, okay? If they had broken them down a different way, that would have been far better, and it would have been a lot easier to see how they got them. This way, you just have to go for it, okay? Actually, I take that back. They do show on page 173 at least a rendition of how they did it. I'm not saying they covered every step, but they covered most of them. Okay. You can follow that. I was about to okay. Yeah, theirs is, they approach it the same way I was going to. I'll do this sort of quickly. I'll try to do it quickly. One thing bugs me about how they did it, though, but we'll let that go. I'll do it the way they did initially. Let's subtract this equation here. Let's subtract 1/2. Well, number one, multiply both sides of the equation by 2. Okay, lose the 1/2. They're not really contributing anything here. So lose the 1/2. Just multiply both sides of the equation by 2. Okay. Kind of don't like it, but now let's subtract M1 V1 final squared from both sides. Okay, yeah. And let's also subtract M2 V2 squared from both sides. V2 final. No, initial, sorry. Okay. So what we have now is M1 times V1 initial squared minus V1 final squared. Okay? Because these disappear and those disappear. Alright. No. Wrong one. These two and those two. These don't. That one's final and one's initial. Sorry. I couldn't read my writing. Okay. So your left-hand side now becomes that equal to M didn't get this right. Those two do go and these two don't. That's where I can't read my writing. Yeah, that's V2. Okay. Got it. Okay. And over here we have M2 times V2 final minus V squared minus V2 initial squared. Okay. Now, what we do here, I'm going to move up here. M1 times okay. Factor this. V1 initial plus V1 final times V1 initial minus V1 final. Okay? Factor it. Sorry. The difference is two perfect squares. Sometimes the difference of their square roots. Over here you got M2 times V2 final minus V2 initial times V2 final plus V2 initial. Okay. Now, in the top equation, we have we also have to rearrange the top equation as well from conservation momentum, that M1 times V I still write it that way. I'm sort of surprised. V1 initial minus V1 final. Wait a minute. Yeah. I probably shouldn't write it under that one because it makes it look like. Let me write it here. M1 times V1 initial minus V1 final is equal to, because I subtracted this from both sides, and let's subtract M2 V2 initial from both sides. That's equal to M2 2 times V2 final minus V2 initial. Okay. Now, if you'll notice here, if you take this equation and divide it by this side here, your M1s go out, and your V1 initial minus V1 final, they go out. Over here, divide these, those go out, and divide these two, and those go out. So what do you have left? V1 initial plus V1 final is equal to V2 final plus V2 initial. Okay? Now, that's what their equation 614 is. Okay? Now, if you go back to initial and final, then that would be V1 initial minus V2 initial is equal to V2 final minus V1 final. And they, for some reason, rearrange that order and make it minus V1 final minus V2 final. And that's how they get this equation here. V1 initial minus V2 initial is equal to the opposite of V1 final minus V2 final. In other words, when you have elastic collisions, you can look at the change of velocities, okay? And they must be equal and opposite. You cannot if it's inelastic collisions, but you can if they're elastic. So before an elastic collision, the two objects move independently. M1, M2, M1 can be less than M2 or whatever. V1I is that way, V2I is this way. And after the collision, the V1 final could be moving rapidly that way, and V2 final could be slowly that way. That looks like that's a reasonable assumption. Okay? I think they've drawn the arrows about right there. They haven't given us the numbers, so you can't say for sure, but after the collision, the object velocities change, but both the energy and the momentum of the system are conserved because they're elastic collisions. Okay. So summary of the types of collisions. Okay. In an elastic collision, both momentum and kinetic energy are conserved. In elastic collisions, only momentum is conserved, kinetic energy is not. In a perfectly inelastic collision, momentum is conserved, kinetic energy is not, and the two objects stick together after the collision so that the final velocities are the same because they just add the masses and keep the same velocity. Okay. I think they've hit that often enough. So here are your problem solving for one-dimensional collisions. We're not talking about glancing blows that they go off at angles. They're one-dimensional. Head-ons or head to tail or something like that, but not glancing blows. Okay? First, set up your coordinate system. Set up the coordinate axis and define, since you're only in one dimension, you only need one coordinate system. So even if it's at an angle or wherever it is, since it's all in one thing, let that be your coordinate axis. X if you want to, Y, whatever you want to, but it's only moving in one dimension. Okay? So coordinate axis, define the velocities with respect to the axis. However you set it up, one velocity is going to be positive, one negative. However you set that up. One direction positive, one negative. You choose that and go, but stick with it. Okay? It is convenient to make your axis coincide with one of the initial velocities. Yeah, that's usually a good idea. Diagram. In your sketch, draw all the velocity vectors and label the velocities and the masses. Okay? Be sure you have everything written there. Let's see. I didn't see you come in, did I? Okay. Yeah, I got it. Yeah. Anyone else come in while I wasn't looking? Okay. So draw your pictures. Pictures are worth thousands of words, so get them down there, okay? Label velocities and the masses. You use the conservation momentum, no matter what kind of collisions you have, as long as it's an isolated system, use conservation momentum. Write a general expression for the total momentum of the system before and after the collision. Equate the two momentum expressions, fill in the known values. They like to do literal equations, then plug in the values. A lot of students like to plug in first and then solve it. Doesn't really matter. Okay, you can only use conservation of energy if the collision is elastic. If you do, then write the second equation for conservation of kinetic energy, or the alternative equation, and that only applies to perfectly elastic. There they said it. Elastic collisions. Okay, if it's not perfectly elastic, it's not elastic. Then you solve the resulting equations simultaneously. Okay, here are samples of your sketches. Draw before and after sketches. Label each object, include the direction of velocity, keep track of the subscripts. So before the elastic collision, this is going to be an elastic collision. Two objects move independently. M1 moving to the right, V1I. M2 moving to the left, V2I. Your positive directions to the right. After the collision, the elastic collision, no loss of elasticity at all, so there's no loss of kinetic energy. After the collision, the object velocities change. The object velocities change, so velocity is not concerned for it, but the energy and momentum are concerned. So looking at it, it's hard to say who wins. I think M2 does, because it looks like it winds up with a greater velocity here than you have there. Okay. Now, if you have perfectly inelastic collisions, here's how the sketches would look. The objects do stick together. do stick together. Include your velocity directions. They've got to be one-dimensional. That's what our assumption is here. The after collision times the masses, because there's only one velocity for the two masses. So you add the masses together and have just one final velocity. Initially, you had mass 1, V1I, mass 2, V2I, but if they don't stick together, if they do stick together, perfectly inelastic collision, then your final velocity is of both masses M1 and M2. The after collision combines masses, they both move with the same velocity, whichever direction that is. That's the picture. I don't really like the velocity arrows because they don't seem realistic. Now, that was that. Do any of you need to see example 6.6 or 6.7? Let's play pool, or 2 blocks in a spring. All right, we're ready for quick quiz 6.7. I didn't miss any, did I? Number going up as high as 6. Oh yeah, I did miss some. Sorry. Let's go back a couple pages to 6.4. An object of mass m moves to the right. See, your right would be that way, with a speed v. It collides head-on with an object of mass 3m moving with speed v over 3 in the opposite direction. If the two objects stick together, what is the speed of the combined object? It now has mass 4m. Okay. Let's get sort of a figure going. Don't ever try to do these without a figure. So let's back up one. And This is sticking together, so what we'll have here, we'll have the top one here, M1 is going to be M. V1 is going to be V. VI. Okay? M2 is 3M. Okay? And the speed is V over 3 in the opposite direction. That's V over 3 in the opposite direction. Okay? I should probably put a minus V3 just so you understand that it's the opposite direction. V over 3. If the two objects stick together, what is the speed of the combined object of mass M, 4M, after the collision? All right. Well, here is the final. M plus 3M, and we're looking for the final velocity, aren't we? What is the speed of the combined object of mass 4M after the collision? Okay. Well, write down your equations. M times V minus V over 3 times 3M. Yeah. Yeah. The initial momentum. Now look at this. One here has mass M moving to the right at V, I. This is 3M moving to the left at V over 3. And that's a minus 3 over V over 3, also initial. So the initial momentum of the system is mv from here in the positive direction, m v over 3 times 3m in the negative direction. So that's a minus sign. The 3's cancel out. You have mv minus mv. Guess what? Initial momentum of the system is 0. So therefore, at the end, your final moment, mass is 4m, but if the final momentum is 0, then v final has to be 0. Okay? So that one looks like it's going to be A. 6.4 A. Got it. Now look at 6.5. This is skaters. I don't draw skaters well. But a skater is using very low friction rollerblades. A friend throws a frisbee to her in a straight line along which she is coasting. Okay? A skater is using very low friction rollerblades. Friend throws a frisbee to her on a straight line along which she is coasting. Now, when you see the word coasting, assume that means constant velocity. Okay? So she is going at a constant velocity. It doesn't say anything about her mass. Describe each of the following events as an elastic, inelastic, or perfectly inelastic collision between the skater and the frisbee. All right? Describe each of the following events as elastic, inelastic, or perfectly elastic collision between the skater and the frisbee. Okay, here's event A. She catches the frisbee and holds it. What would that be? Would that be an elastic collision, an inelastic collision, or a perfectly inelastic collision? What would you say? Skater is using very low friction rollerblades. A friend throws a frisbee to her on a straight line along which she is coasting. She's going this way, and the frisbee is coming in that direction. So there's no angles involved. Okay? Describe each of the following events as either elastic, inelastic, or perfectly inelastic collision. Elastic. Perfectly inelastic collision between the skater and the frisbee. She catches the frisbee and holds it. Perfectly inelastic. That should be your, well, I guess that's perfectly inelastic. I thought they were looking for an A or B. A is perfectly inelastic. Perfectly inelastic. B, she tries to catch the frisbee, but it bounces off her hands and falls to the ground in front of her.
Be elastic
Well, what gives it away is it bounces off her hands and falls to the ground. So that would be inelastic, not perfectly inelastic. Okay? B is inelastic. The C one, she catches the frisbee and immediately throws it back with the same speed relative to the ground to her friend. That would be elastic. Okay? Oh, trying to represent elastic. Let's see. Y'all made it in time for lap. Okay? So let me go on and mark the roll for today. Yeah. No, 2 to 3. Yeah, okay, that's right. If A is still here, there you are. Okay. Nick is still here. Kiara is still here. Courtney Brooks is still here. Raven just got in. Shakina isn't going to make it today. Something major happens to her. Charity, we haven't seen in forever. Courtney Humes is still here. Amber's still here. Essex is still, Essex is still here. Yeah, Ryan's still here. Already got Ryan. Okay. Darius is still here. Monique is still here. Sasha's still here. Allison's still here. Darius is still. Wait, did we lose Darius? Looks like we did. So he's not still here. Scarlett's still here. Will's still here. Brianna's still here. Naya, you said wasn't coming in today, right? Okay. Bria just came in. And Dakota's still here. All right. Let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah. Okay. That was the 6-5. We got that. 6-6. In a perfectly inelastic one-dimensional collision between two objects, what initial condition alone is necessary so that all the original kinetic energy of the system is gone after the collision? I know what they're getting at, but boy, that question is so bizarre. In a perfectly inelastic, one-dimensional collision in which between two objects, what initial condition alone is necessary so that all the original kinetic energy of the system is gone after the collision? Okay, here's A. The objects must have momenta with the same magnitude but opposite directions. The objects must have the same mass. The objects must have the same velocity. Or D, the objects must have the same speed with velocity vectors in opposite directions. That certainly would be enough, I think. Yeah, it's a perfectly inelastic collision. That would be enough. The others are not necessarily going to be the same. So they didn't say anything about the masses being equal. That's what I was trying to read to make sure they didn't. So this would be A. You're absolutely right. Okay. Now let's go to glancing collisions. All right, 6.4. For a general collision of two objects in three-dimensional space, the conservation momentum principle implies that the total momentum of the system in each direction is conserved. So now your equations have to do this. Now, actually they said three-dimensional space, but they only gave you two dimensions, x and y. So I wish they had said two-dimensional space. That would have fit this what they're saying better. M1, V1, Ix, now we have three subscripts here. V1 for object 1, I for initial, and X for the direction, plus M2, V2, Ix. Okay, so that's the total momentum of the system in the X direction is equal to M1, V1 final X plus M2, V2 final X. So that would be saying that the X components have to add up and equal. The Y components, M1, V1Y plus M2, V1, VIY, M1, V2, VIY, 2 VIY must equal V1, M1, V1 final Y plus M2, V2 final Y. Okay. Now you use the subscript for identifying the object, the initial and final velocities, and the components. So that's why you need all three in there. Now they said three-dimensional space, they only did two-dimensional space. If you had three, then you'd have one more that said M1 VIZ plus M2 V2 IZ equal M1 V1 FZ and plus V2 M2 FZ. Okay. So here is here it is. Bottom of page 176, figure 616. Here we have mass M1 with velocity V1I. Stationary mass M2. Okay? Now they've drawn this intentionally so that if M1 is coming like this, it does come close enough that it actually impacts M2. Okay? X directed that way, Y that way. What's your VI, V1IX? It's V1I. Everything's in the X direction there. What's your V1 IY? Be 0, because there is no initial velocity of ball 1 in the y direction. All the velocity is in the x direction. What's V2IX? V2IX? Zero, it's not moving, it's stationary. V2IY? 0 also, it's not moving up and down either. It's stationary, okay? Now, after the collision, ball 1 heads off at some angle theta, okay, with a final velocity of VI times the cosine of theta, that's in the x direction. No, that is the direction this way, VI cosine theta, okay? Now you can break that into a horizontal component and a vertical component. No, okay, so you have done it here. Your final velocity is VI final in this way. It has an x component or an I component, x component, VI LX is VIL cosine theta. Whatever that velocity, final velocity is times the cosine of theta, and this one's the sine of theta. If this is theta, that means that's theta, cosine would be adjacent over hypotenuse, sine would be opposite over hypotenuse. So that's what you got there. Your M2 takes off with the V2 final in this direction, and its x component is V2 final times the cosine of phi. This is angle phi now. It doesn't have to be the same as theta. And that's angle phi, so the cosine, the x component would be V2 final times cosine phi, and the y component V2 final sine phi. Now, looking at that, can you come up with a couple of equations for me? Let's go to the component at a time. The x component here is V1I. That's all you got. So M1, V1I, that's the total momentum of the system in the x direction. And that's equal to total momentum in the x direction here, which is V1 final cosine theta plus V2 final cosine phi. Okay? So this M1, V1I has to equal M1 V1L cosine theta plus M2 V2L cosine phi. Those are in that direction. In the vertical direction, 0 to begin with. Okay? Finally, M1 V1L sine theta plus M2 V2 sine phi, they have to add to be 0, which means that this obviously is a negative f direction, so sine phi here is a negative quantity. Okay, sine theta is a positive quantity, so that makes them opposite. So with just the magnitudes of those, V1, M1, V1L sine theta has to equal M2, V2L sine phi if you just use the magnitudes. They have to be equal because we know they're opposite. The after velocities have x and y components, the initial does not. Momentum is conserved in the x direction and in the y direction, but initially the y momentum was 0. So that's why those two add to 0. Apply the conservation of momentum separately to each direction. And that's what I just described that you did. Okay. So, problem solving for two-dimensional collisions. Again, set up your coordinates. Set up both the coordinate axes and define your velocities with respect to those axes. It's usually convenient to choose the x or the y axis to coincide with one of the initial velocities. Okay? In our previous problem, you only had one initial velocity. Make that your x in that direction. Okay? Thank you. Draw your diagram. In your sketch, you show before the collision, after the collision. Draw and label each velocity, each mass. Now, I really didn't think they did a good job of doing the masses here, but they had colors in it. So once you had M1, then you had M1, and this is M2. But they didn't actually write those equations that way. Okay? So in your sketch, draw and label all velocities and all masses. Conservation momentum. In this case, you have to write expressions for the x components of each object before and after the collision, and keep the x's together and do the same for the y's. Write expressions for the total momentum before and after the collision in the x direction and in the y direction. Write expressions for the total momentum before and after the collision in both. Okay. The last one we did had none initially in the y direction. Conservation of energy if the collision is perfectly elastic. Now that problem, I don't think, made any statements about what kind of collision it was. So you can't assume it's perfectly elastic unless they tell you. Okay? Because nothing there indicated that you could. You know it wasn't perfectly inelastic because they didn't stick together. Okay? But there's nothing in the problem that indicates it would or would not be perfectly elastic. If it's not perfectly elastic, you can't use conservation of energy. If it is perfectly elastic or just elastic, you write an expression for the total energy before and after the collision. Equate the two expressions, fill in the unknowns, solve the quadratic equations, and they say they can't be simplified. Remember to skip this step if the collision is not perfectly elastic. If it's not an elastic collision, don't try to do anything with energy. You can't. Solve for the unknown quantities, solve the equations simultaneously. There will be two equations in the elastic collisions, three equations for any elastic. Okay. Now they have example 6 there, collision at an intersection. That would be a glancing collision. 6.5 is talking about rocket propulsion. I like to back up maybe just a tad before we get to it. What was the first heavier than air flight? Well, I don't know. Yeah. What was the first flight leaving the ground? What was the first thing that man was able to do to get to leave the ground? Before they had airplanes, before Orville and the Wright brothers. I can't remember the other one's name. What type of air travel did you have? Generally not very far and couldn't control it super well, but they could travel around in balloons. Okay? People did actually do that. Some. Very limited. Now, let's think of a balloon. Blow up a balloon and hold it by the nozzle and then release it. Okay. You're holding it by the nozzle. You've got air in there. What's the momentum of that system? You're holding it. Still. 0 because it has no velocity. Okay? Now, You release that nozzle, and what happens? You didn't tie it off, you just released it. What does the balloon do? It takes off, okay? If you're holding it up, it usually goes up to begin with, or holding it like this, it goes that way. You just hold it. Why does it do? Well, you have air rushing out of this end, and the balloon then must move forward at that end. Conservation of momentum. Now, you know it goes a little crazy, and the reason it goes crazy is you have a flexible nozzle. So whenever the nozzle flexes, which it does when the air is rushing out, turbulent flow, it makes it wobble, and then so the balloon goes all over the place. But at any moment, it is conservation of momentum. Okay? Now, what was the next type of air travel? Now think Wilbur and Orville. I remember his name. Prop planes, propeller-driven planes. What is making that plane fly? It said it's propeller-driven. What is propeller-driven? It's pushing air backwards, right? Because the propeller comes through the air, it has an angle, they call it the pitch, and as it spins, it's pushing air backwards, so therefore the plane is being pushed forward. Conservation momentum. The same mass times velocity of the air being pushed this way, mass times velocity of the plane is that way. So obviously it's pushing that air back really fast because the plane is much heavier, has a much bigger mass. So it's pushing the air back there very rapidly. So after we had propeller planes, what did we have? Jet planes. Okay? So what is a jet plane doing?
Pushing air backwards.
Okay. You're burning the fuel, and the burning fuel, the exhaust is shooting out the back, and that pushes the plane forward. So again, you have conservation momentum. And those gases are really flying out the back. I mean, very high rates of speed. Some mass times velocity forward, mass times velocity back is equal to mass times velocity forward. Now, let's think back on propeller planes. Because you're having to push the air backwards, then there's a limit to how high you can go. Because guess what? The higher you go, the less dense the air gets. There's just not as much air to push. And if you don't have enough air to push, you can't move forward. Okay? So you're limited to how high a propeller-driven plane can go. With a jet plane, what's moving backwards is the exhaust. So the faster you burn the fuel, as long as you can get enough oxygen to burn the fuel, yeah, so jet planes can go much, much higher. In fact, the higher you go, the less air resistance you have. So there is a limit. You have to have enough oxygen to burn the fuel. Okay. Now, let's think about rockets. Depends on what type of rocket, but generally a rocket, let's think of the NASA rocket, what do they do? Okay, they're going up. So now you've got a little bit worse because you're having to overcome gravity too, whereas that everything else is if it's horizontal flight. So here we're going up. So what have you got? You've got your fuel and the oxygen source both in the rocket. So now you're unlimited with how high you can go. You can even go into outer space where there's no oxygen, but the mass times velocity of the air down, the exhaust down, equals mass times velocity of the spaceship upward. And to launch those big old hairy things that are huge, you have to have a lot of force. And you've seen it. Those engines are just blasting downward, pushing it upward. So the operation of a rocket depends on the law of conservation of momentum as applied to the system, where the system is the rocket plus the ejected fuel. A lot like it was with the jet plane too. This is different from propulsion on the Earth, where the two objects exert forces on each other. Okay? So what they're saying here, the system of the rocket plus the ejected fuel. So the ejected fuel is actually going out the back, moving the rocket forward. It's not pushing against anything. Whereas propulsion on the Earth, the two objects exert forces on each other. Road on car, train on track, whatever you got there that's doing that. So this is just hot gases going out and the rocket going up. Again, very similar to jet flight 2. The only difference is with a rocket, you have both the oxygen source and the fuel, whereas a jet, you're depending on the environment giving you oxygen. Okay, the rocket is accelerated as a result of the thrust of the exhaust gases. That's what does it. Guess what? The gases aren't pushing on the Earth. That's not what's happening. They do hit the Earth, but that doesn't affect that. It's the speed at which they're going out, the mass times velocity equal mass times velocity upward. That's all. This represents the inverse of an elastic collision, inelastic collision. Okay, what do they mean by that? Inverse of an inelastic. Oh yeah. You start with the gases are inside the rocket. So you start with them together, and now you separate them, and the gases go this way and the rocket goes this way. Whereas in an inelastic collision, you start with them both having velocity, but you end with them together. So that's what they mean inverse. Weird way to say it, but yeah. Momentum is conserved in every instance. Kinetic energy is increased at the expense of the stored energy of the rocket fuel. Yeah, technically that's true. But in reality, your kinetic energy, the rocket upward, is at least, I don't see how they say it's increased, but I guess it is. Because you are changing chemical energy in the rocket fuel into kinetic energy of the gases. So I guess that's what they're saying. Okay. Because energy changes form so rapidly, and that was internal to the system, so that's correct. So here is the rocket propulsion. Now, here's a problem with it. Okay. Because you're burning your fuel and you're using, to burn it, your oxygen supplies, your mass is always changing. Before this, we assumed the mass was the same. It's not changing. But because you're firing out masses of gases in the rear, you are losing mass in the rocket ship. So your velocity is in that direction. So m plus delta m, which is usually a negative quantity, times v, that would be your momentum, initial momentum. M plus delta m times v. The initial mass of the rocket is m plus delta m, where mass of the rocket and delta m is the mass of the fuel about to be burned. Okay, so I'm sorry, capital M is not the total mass, it's the mass just of the rocket. And delta m is the mass of the fuel you're about to burn, which could involve your oxygen supply as well. Okay, and the initial velocity of the rocket is v, as stated. Okay, now if you're burning the fuel here, and that's your delta M that you're losing, then your final propulsion, the rocket mass is just the M part. The delta M is now going out the back. The mass of the fuel, delta M, has been ejected at a very high rate of speed, by the way, so that V out the back is not nearly long enough, okay? The rocket speed is increased from V to delta V. They don't define that very well. It's certainly not the same as the V over here, okay? Is the increase of momentum. Okay. The basic equation for rocket propulsion then is V final minus V initial. Now that would be for the rocket ship itself. This is velocity of the exhaust. This is only for the rocket itself. V final minus V initial is equal to V of the exhaust times the log of the mass initial divided by the mass of the fuel. Mi is the initial mass of the rocket plus fuel. That's what we were calling M plus delta M. And M final is the final mass of the rocket plus any remaining fuel. So you are allowing that you wouldn't burn it off. The speed of the rocket is proportional to the exhaust speed, obviously. Okay? For best result, the exhaust speed should be as high as possible. Typical exhaust speeds are several kilometers per second, so very, very high rates. Now, a lot of rocketry then is involved with designing the nozzles. Okay? Let's go back to the picture. And they just have generic looking nozzles here. But a lot of your design goes into how these are formed. Because of different shapes and sizes and changes of openings, that determines how much velocity of the exhaust you got. So it's that's where a lot of the science in rocketry goes, is in designing those nozzles. Okay? Now, what do we mean by thrust of a rocket? The thrust of a rocket is the force exerted by the rocket on the rocket by the ejected exhaust gases. So the instantaneous thrust would be given by the mass of the rocket times the acceleration of the rocket, the mass of the rocket times the change of velocity over change of time, that's what acceleration is, which is now the absolute value, if you take it from the last equation, that equation there, okay, where your delta V is your V final minus V initial, you just multiply by mass times that, okay, and that is VE, oops, too much, times, well, you can't really tell it from that one, okay, delta M over delta T, okay, this is the change of the mass, in other words, how much you lost in your, by the fuel that you burned over change of time. Because velocity times the change of mass, that's what's moving. That change of mass, that's your exhaust. And that rate there is that the thrust increases as the exhaust speed increases, and the burn rate, which is delta M over delta T, increases. So that's called the burn rate. Now, sort of hidden in this is the fact your conservation of momentum is almost evident here. Because if you think of this as mass of the rocket times mass velocity, change of velocity of the rocket, that's your change of momentum per change of time. And this is your delta M, is the stuff that you burn times the exhaust, that's your change of velocity for change of time. So sure enough, that says one force equal opposite to the other force. It's basically Newton's third law as well as being conservation of momentum. And that was and is the last slide. Okay. Now we've still got about 15 minutes. We didn't really have a break, did we? Okay. Got 15 minutes, not counting the 10-minute break that we didn't take. We really got 35 minutes. So if you want to keep going, then you can leave today at the 4:50 mark. Or if you want to take a break, we can do that now with, so little time left. Don't you want to just go on and finish a little early? Okay. All right. So let me. What's that? What about for this chapter? Oh, okay. We'll get those at the end. If we take time now, then we'll have to go longer. So yeah, I'll have 10 minutes at the end. I can pass those out. So I hope everybody that does need it is still here. Thanks. I'm sorry? No, that's what I'm giving you back.
Okay.
Now, let's just talk a little bit about what we're going to do next time. Thank you. What we'll do now, I'll finish up here, so let me go and do that. There is an applying physics 6.2 multi-stage rockets that you can read about. It's pretty good. Example 6.9 is single stage to orbit, SSTO, is that example. I'll be glad to go through that if you'd like to see. The summary 6.1 has at least 3 big equations. There are others, but you'll have to catch those back in the sections. Some definitions, a theorem or two. 6.2 conservation of momentum. Momentum is conserved in every collision. 6.3 was collisions in one dimension. So they give the types of collisions, elastic, inelastic, that type of thing, perfectly inelastic. Then there's glancing collisions. They don't give any equations there, but there are some in the text. You'll have to go back and see them. And then rocket propulsion, you had a couple of major equations there. Conceptual questions, the odd number answers are in the back of the book, so you can read through those. The problems, these are going to be closest to what your test questions are. For 6.1, any of the odds 1 through, because they give odds in the back, 1 through 19. They have a bunch of those. 6.2, odds 21 through 29. 6.3 and 4 they put together. 31 through 53, a whole bunch of those. And then 6.5, rocket propulsion, 55 through 59. Then they have some other examples, and there are various kinds of these, some biologic, some others. You can do any of those you want, 61 through 85. Okay, quite a few of those. All right, and as I said, we're skipping topic 7, rotational motion and gravitation. Wish we had time for gravitation, that would be good too. Then we have rotational equilibrium and dynamics, that's topic 8. Wish we had time for that, that's a very good topic. Now, many of you engineering majors, pre-engineering, not so much, so you probably aren't going to need too much of that. However, I think a lot of you are probably physical therapy majors, is that right? Some of you? Okay. There is a little bit of rotational stuff involved with that, but not usually on the physics side. It's just more of the motion side. Okay. But that's... Oh, wait, I'm going too far. That was topic 8. Okay, so now we're into topic 9, which is fluids and solids. I think we only do one chapter on this. And then we get into thermodynamics. And we'll end with thermodynamics just as far as we get. We'll just go with it, I think. I don't think there's anything after thermo that we do. I can't remember. Are we supposed to do a section on vibration waves? I can't recall. We may not have time. You know, our term got shortened from a 10-week term to an 8-week term because we lost 4 Mondays. Memorial Day, the Monday I had to be in New Orleans because the vice president didn't want to do it on a weekend. The governor gave us an extra Monday for 4th of July weekend, and then the dean took away last Monday. So I can't remember if we were to do vibrations and waves in this class. Does anyone recall? Yeah, on the course description. It seems like we do this in 202. Well, if we do, we may skip one of the, thermo chapters. Let's move into fluids and solids. This is topic 9. And I must have hit too many spaces there while I was trying to figure out. Okay. Topic 9, solids and fluids. Topic 9 is fluids and solids. Chapter 9 was solids and fluids. It doesn't really matter which way we go. I swear this takes so long. Okay, what I was going to say, what we'll do, we're going to go as far as we can in topic 9 today. Then on Monday, and we will have class 2 days next week, knock on wood, okay? Unlike the last 2 weeks when we've only had 1, okay? So we'll do the first hour and a half continuing topic 9, and then the last 2 hours we will do the lab for topic 1 we just finished. What was that, 7? 6, the momentum lab. Okay. So let's get going. Slideshow from current slide. So chapter 9 was solids and fluids. Topic 9 is fluids and solids. It doesn't really matter. Now, I'm a little surprised at this. We used to always call these states of matter. But once quantum mechanics came into play, I thought physicists quit calling these states of matter and started calling them phases of matter. And in fact, most other books I've read, this book happens to keep calling it states of matter. Yeah, we know what it's talking about. If I said, how many states of matter do we have, what would you say? Second? 3. What would they be? Solids, liquid, and gases. In reality, there are 4. They just listed separately. Plasma is another phase of matter or state of matter. Okay? Solids, liquid, and gases predominate on the Earth. Plasmas predominate in the universe. If you think of our solar system, what is most of the energy in our most of the matter in our solar system? Okay, let's back off. Okay? What does it mean to be a solid?
Your like molecules, like the atoms and stuff, like they don't move. Some of that.
Okay. Before quantum mechanics, we would have said that's exactly right. Sounds like quantum mechanics are here. Everything always moves, but the very limited motion. Okay? What that means is the atoms, you're really getting awfully close to it, are in a fixed crystal structure. There is motion, but it's all vibrational. That's all you can have is vibrational motion in a fixed crystal structure. You have no rotational motion. You have no lateral motion. It's all vibrational motion. That's the only kinetic energy you can have. Okay? Now, how do you change a solid typically to a liquid?
Liquid, like
how do you change it?
Melt.
Okay, you typically add heat, add energy to it. What does that do? It breaks down the crystal lattice that is holding that together, and now you have freed those bonds, so now the molecules stay close together, but they're not attached in a fixed status. So a solid has a fixed volume and a fixed shape. A liquid has a fixed volume because they stay close together, but now it has a variable shape. There is no positional structure anymore, no crystal lattice. So you've broken that down with adding energy. How do you go from a liquid to a gas? Add more energy, exactly. And now what you're doing, you're breaking the positional, the cohesive forces that are holding those molecules together, and now they're free to go everywhere. So for a gas, it has no fixed shape, nor does it have a fixed volume. It doesn't affect anything. If I had a bottle of ammonia over here, and were to come back here and open it, and then I say, y'all carry on, I've got to go to my office for a minute. After a while, y'all would be smelling the ammonia pretty strongly, and then y'all would be, and finally, Courtney would be, these people would be passed out, but you would finally be smelling it, because the ammonia will take up the volume of the whole room. It takes a while to get there, but it would. Same with perfume or anything else that is a gas. So how do you think you go from a gas to a plasma? What would be a good gas?
Heat.
Add more energy, exactly. It doesn't have to be heat, but add more energy. Is there any plasma in the room? I see solids. I know of some liquids. We're mostly liquid. Lots of gases in here. Are there any plasma in the room? What's in these fluorescent tubes? Plasma. You have added energy, electrical energy, big capacitors in the ballast of these, given a lot of it, and now what have you done? When you add energy to a gas, typically what you do is knock off or add electrons. That's what's happening here. The ballast, the capacitors are picking up charges or losing charges. So now you go from being a neutral gas to a charged plasma. Okay? That will have positive or negative ions, and that's what's flying up and down those tubes. And as they fly past with high levels of energy, that white powder, have you ever broken one of those tubes and seen that white powder? That's a phosphorescent material, and as the energy goes by, it jumps up a photon, an energy level, and then when the energy goes by, it falls back down. That gives off the light, because the phosphorescent material is such a material so that the photon of light that's given off is exactly the right frequency and stuff to happen. So that's what's happening in the plasma. So in our solar system, what do you think we've got more of? Solids, liquids, plasma, gases, or plasmas?
Plasma.
Where?
In the solar, in like our space, solar system.
But where would it be in our solar system?
Sun.
The sun is just about totally plasma, and the sun has more mass than anything else. All the rest of our solar system added together, nowhere close. I think the sun is 800 times more massive than everything else in the solar system added together. All the planets, all the moons, all the asteroids, all the comets, everything in the solar system added together is nowhere close to what the mass of the sun, and the sun is just about all plasma. So yes, plasma dominates the universe, because all the stars out there and other things. Now, the only thing that, to me, makes a little bit of a problem here, all this talk they have nowadays of dark matter, that's going back to being solid again. That's not plasma. And if the dark matter predominates over the actual stars, then we may actually be more things. But it says here, it says it predominates the universe. So this chapter introduces the basic properties of solids and liquids. Now, back off there. What's the name of the chapter? Fluids and solids. What is a fluid? Fluid is either a liquid and or a gas. The air coming out of this vent, that's fluid flow. The water coming out of the spigot, that's fluid flow. So I don't like to say solids and liquids, they should say solids and fluids. And that includes some properties of gases, which of course are fluids also. We have hit the magic hour, haven't we? We will start next time with solids. But I've got to find where solids are here. Okay, I guess it's right there. Okay, good deal, folks. So next time we'll only go approximately an hour and a half of class, and then we'll do 2 hours of lab. That'll be, is that right? No. Yeah, that's right. Hour and a half.
Test 4 and 5.
Okay, test 4 and 5. Okay. Let me go on and shut this down.